Okay, well, great. Well, thank you all for taking some time today to listen to what my biased opinion would say is one of the, if not the most important topic in renewables and the energy transition right now. So we'll be talking about critical minerals and why utilities should care. So before I dive into the first slide, just want to throw out some food for thought. So in 2021, of all of the new electrical generating capacity installed in the United States, 70% of it was wind, solar, and battery backup, for that capacity. And that is a trend that is likely going to continue. We don't have a lot of nuclear power plants slated to be built. We don't have a lot of natural gas combined cycle plants slated to be built. The bulk majority of it is going to be wind, solar, and batteries. And of course, there is the whole EV, electric vehicle revolution that's taking place. We're seeing large uptake of folks buying electric vehicles. A lot of auto manufacturers committing to having a number of electric vehicles available. So keep that in mind. We are transitioning to a non-fuel energy source. So it's very easy to assume, well, we don't have a fuel source like for our natural gas combined cycles. We don't have fuel like uranium for nuclear. So that's why renewables are great. There's no fuel, but they are very metal intensive and very critical mineral intensive. And of course, because of the intermittency of these types of renewables, you're also having to build out a lot more of them. So while you don't have the fuel cost per se, you're having to build a lot more, and every single one of them requires critical minerals. So with that context, let's start diving into the topic at hand. So first and foremost, this presentation is meant to be a high level overview. We're going to deep dive a little bit, but really just want to get everyone on the same page. What is a critical mineral and why are they important? So let's start with what is a critical mineral. As I mentioned, this transition is going to require a multitude of critical minerals, and the United States fairly regularly will update the list of what they deem as being critical minerals. Currently, there are 50 critical minerals listed by the United States. Most major countries have also got critical mineral lists as well. So a critical mineral is essentially a commodity that has very important uses. Mostly those uses, or at least a good portion of those uses, have some application towards defense, which is why the government takes a very active role and takes them very serious. But not only do they have these important uses, but they have no viable substitutes, and they face potential disruptions, usually geopolitical, but in many cases they face disruptions just because there is a lack of potential resources that are available. And when I say there's no viable substitutes, there's a handful of individuals who would argue, take rare earth elements, and we're going to dig a lot more into rare earth elements, but you use rare earth elements for a lot of things, but namely it's for permanent magnets. And oh, we got a question. Oh, sorry, I thought I heard a question, but you take rare earth elements. Oh, sorry, can repeat your question? Oh, not sure I heard the question. I'll keep going. So anyway, so so you take a permanent magnet, for example, that uses rare earth elements. For many, many, many decades, or at least many years, they've been trying to find viable substitute for these rare earth elements and these permanent magnets. They've been unable to do it because these elements are so unique. It's very, very hard to substitute them out. And you're going to learn, hopefully by the time we're done, why they are so unique and hard to substitute out. So we call them critical minerals, but they include both minerals, such as barite, and you don't need to go back and remember what barite is, but barite is an actual mineral. And then you also have elements that are on the list like dysprosium, which is a specific rare earth element. So it's a mixture of the two of them. All critical minerals must be mined. There's no other way around it. You could argue you can recycle them. We do some level of recycling of some of these elements, but the volume and the ability to recycle is one, currently uneconomic, and two, there's just not quite enough volume to really put a dent into the supply and demand of these critical minerals. So all of them must be mined right now, and it's really not pretty in most parts of the world. So while I am a huge proponent of mining these critical minerals, I'm a much bigger proponent of mining them sustainably. So what you're seeing right now is a good example of the challenges that renewable energy and the transition are going to face as far as the supply chain goes. So you look at lithium production in Chile, a huge majority, a huge majority, at least a vast majority of the lithium that's produced today is produced with these big evaporation ponds. We're not going to go into a lot of detail, but they do take millions upon millions upon millions of gallons of fresh water that are brought to the surface with wellbores, evaporated over the course of a year or two. And then you see the different colors because they're at various stages of lithium concentration. Rare earth element refining in China, very few environmental regulations there. You see this picture of a lot of the acid that's used to leach the rare earth elements. They dump them into these big lakes, and they are incredibly toxic. If you go and visit these areas, your eyes can literally burn just because of how toxic the materials are getting dumped without any sort of liners, without any sort of environmental precautions. And probably the biggest one that's been in the news the most is cobalt mining in the Democratic Republic of Congo. While the small scale mining that uses this kind of labor is not the majority, it's still a large percentage. Something like 20% of the cobalt is still coming from these small mines where they're using very unsafe practices. It's a very dangerous prospect to mine cobalt in the DRC right now, especially if you're in a small village. So there's a lot of challenges, but there's also a lot of opportunities, because while you mostly hear about the very negative mining operations out there, there are some incredible innovations that are taking place. And so we're going to talk a little bit more about that as we move forward in the presentation. So before we really start talking about energy, I want to draw your attention to something that we can all very much relate to, because I guarantee that at least half of you are multitasking. You're checking your Instagram right now while you're listening to this. So you've got your iPhone. And so, critical minerals are literally in your hands. And I like to show this picture from the USGS of the rocks or the minerals that these critical minerals come from, just so that it really stays in your mind. These are natural resources. These are rocks that actually need to be mined and come out of the ground. So, but these critical minerals are the whole entire reason. There is no other reason that our phones and our computers are becoming smaller and more powerful and faster. It is because of these critical minerals. So our touchscreen, for example, very innovative. We all wouldn't know what to do without being able to interact with our phone on a touchscreen. And that's thanks to an element called indium, which is a transparent conductor between your phone and your finger. And that conductivity is what allows you to drag and drop and move things around on your phone. Europium and terbium. So there's a lot of these critical minerals or critical elements that have very bright hues. They allow things to pop. Like when you look at whether it's LEDs or an LCD screen, it's these critical minerals that allow for such great color quality. And then you have like tantalum that regulates the power in your phone. Of course, you've all heard a lot about lithium, nickel, cobalt. We're going to dive into that a bit more coming up. But that's what's storing the power in your phone. So why you can get through a 10, 12-hour day multitasking on your phone, and you don't have to sit and recharge it all the time. Cerium is another rare earth element that's used in polishing the glass. So when you fill your touchscreen on your phone, it's super smooth. That's because it's being polished by a rare earth element. And then even in the sound system. So not a lot of people think about when they're listening to their phone and they can hear mom or dad or their boss on the other end of the line. The reason that you can hear them is because of the vibrations that are being created because of the rare earth elements in the magnets that are actually making those sound waves work. So everything in your phone is working well. It's fast because of these critical minerals. So That's just a very tangible thing, because some of us have never seen large offshore wind turbines. Some of us have never driven in an electric vehicle, but we can all associate to a phone. So these minerals are everywhere. Think about this. In the 1990s, Intel used only 15 elements to build their computer chips. Today, they are using 60. So when we hear about these chip shortages are in part because they require so many different elements that are spread throughout the globe, and some of them are in such limited supply that we've created this chip shortage. So things are definitely getting a lot more complicated as far as the critical minerals that are being used in the systems we're deploying. So let's talk about some of the primary challenges. So first and foremost, for the United States, for over half of those 50 critical minerals on the list, we are 100% dependent upon other countries for their mining, for their production, for their refining, etc. And I will say the other 50% of those, the majority of them were still reliant to at least 75% for those materials to come into the United States. China is the largest supplier of these critical mineral products to the United States. And after that, we have Canada, who supplies quite a bit of elements. Canada's got a very friendly, very mining friendly ecosystem. So that's fortunate for us since our neighbors to the north, and similarly with Australia. So the United States is currently in a process of building these coalitions with these friendly countries to really help the growth of our critical mineral industries. So think about this. The IEA estimates that critical mineral production collectively for the energy transition will need to increase by 400% by 2040. And then to hit the Paris Accord goals, 600% to be net zero by 2050. We mine a lot globally. So to talk about collectively increasing all of these minerals by 400 to 600% is a feat that might be one of the most incredible feats that we've ever had to face as a species, to be able to actually mine this much material. And we're going to dive a lot more into some of the specific growth needed in these elements. There's another challenge, is this geographical concentration for production and refining. So if we take the popular ones right now, lithium, cobalt, rare earth elements, the top 3 producing countries control 75% of the global market. So I want you to all think about this. Think about the geopolitical turmoil that we've gone through over the last several decades with our oil markets. And oil is produced in large quantities between about 15 and 20 countries around the world. And yet we still have wars that are fought. We have a lot of geopolitical issues over our oil. For these critical minerals that are completely dependent upon these, getting our renewable systems deployed, we're talking about 3 or 4 countries that control the vast majority of the supply chain. So let's think about geopolitically the problems that could cause if the United States is not proactive in developing a domestic resource for these critical minerals for our energy transition. So in the United States and in other Western countries, the average time to get a mine up and running from exploration to first production is 16 and a half years. Oftentimes it's much longer. There's certain mines right now that are under permitting. They've been under permitting for 25 years in the United States and still have not seen any significant production. So that is a huge problem, are these lead times. Think about the quotas that these auto manufacturers, or think about all the utilities and the solar panels, the wind, the battery backup that they've got in their IRPs. There's a good chance they're not going to have the materials to hit those goals that they have laid out for themselves over the next 5 to 10 years, because these mines can't keep up with the demand. That is a huge problem. And maybe one of the most challenging problems, and this is where innovation is really coming into the mining space right now, is global resources are experiencing declining grades. That means that the percentage of the critical element that you're trying to mine in the volume of rock that you're excavating is getting smaller and smaller and smaller. So that means you need to mine more rock to process the same amount of that critical mineral. And we're going to talk a little bit more about that here coming up. And then, of course, we've got a big ESG momentum. There's a big wave going through the investment space. And given the nature of the mining industry, some of these ESG standards are very difficult to track and enforce in the global mining operation. So that's another thing that's being tackled right now and causing some challenges. So let's look at the list of critical minerals. These are the 50 critical minerals that the United States deems as being very much at risk for disruption. Okay, you'll see that on the left-hand side, all of those are 100% dependent. On the right side, these are the ones we're not 100% dependent, but you can see them that at least most of them we are dependent 50% or more for these critical minerals. Now, I've circled the ones that are very much critical to energy. There are a lot of them. In fact, there are some that I haven't circled that are still very important to energy. I could essentially circle every single one of them, and each one of these critical minerals would play some role in energy. But the ones I've highlighted are kind of the big ones that you hear a lot about in the news. So there are a lot that we really need to be focused on, and the majority of those we're 100% import reliant. Here's another cause for concern. When we look at the critical minerals that we need for our energy transition, 50% of them are co-products or byproducts of some other commodity. Okay, so what that means is if you take a base metal, say like iron or nickel, aluminum, something like that, you're going to get something like cobalt or tellurium. Tellurium is very important for solar panel production, but it is only produced when as a co-product from mining for copper. Okay, so now we're all of a sudden getting dependent on critical minerals that there are actually no mines specifically mining that product. You've got to hope that they're going to recover them when they're mining these bigger base metals. So that's another threat. You know, right now you're not going to go. Oh yes, question.
Sorry, yeah, can I get two quick? We had two quick ones I wanted to get in, and the first one I think you might have just addressed on the previous slide, but of that list, I think you might have had it. So someone asked if we had any known sources for that in the U.S. Like, is it all imported, but we could be producing this here and we're just not, or are these things just not even available in the U.S. if we wanted to?
Yes, yes, and yes. So we do have almost every single one of these critical minerals. We have deposits in the United States. And we'll talk more about that in some slides that are coming up.
Okay.
But you know, there's a few of them that you have to be in Brazil. Certain parts of the country just have much more economic, huge resources, so it makes it hard to compete. But generally speaking, the critical minerals needed for the energy transition we have here in the United States and certainly within North America.
Okay, and there's one other. Brian asked this a little while ago, and I'm not sure if this is where this will come back into play in the presentation, but it's a good question, Brian. Where are we in terms of recovering, those minerals? Like you said, the picture of our phones, and do we have anything in terms of sort of life cycle process going where we're getting better about pulling the minerals back out of other products to use, or is that just years behind?
It is years behind, unfortunately. So the vast majority of electronic waste ends up in urban landfills, most of the time outside of the country. So you have this urban mining movement, and unfortunately, it's not well organized. There are a lot more recycling companies popping up. Take Redwood Materials, for example. But you've got to remember, it's still a very early market for recycling because the volume's not there. So when you hear Redwood Materials, they're recycling the low-hanging fruit. So when you open up a gigafactory, for example, you're going to see about a 30 to 50% waste of that lithium product and some of the other products because they get contaminated, they don't meet the spec. And so that's the low-hanging fruit these recycling companies are chasing right now, is just getting that excess material not being used at the gigafactories. Okay. We also don't have a lot of EVs on the road relative to putting a dent in the recycling space. So in the next 10 years, as you see more EVs come to the end of their life and you get a battery that's ready to recycle, you're going to start to see a lot more recycling. But even then, a lot of the research I've seen shows you're not going to have much more than a 5 or 10% impact to the mining side of it from recycling till about 2035. So we were a very long ways off from having a big dent in our natural resource use satisfied by recycling. So there are a lot of companies working on it, but again, to recycle, it's a very expensive process, very energy intensive process. You have to set up hydrometallurgical processing to more or less extract the cobalt or the lithium or the manganese, etc. And the batteries aren't all created the same. There's a lot of energy to pull them apart. And if you set up a recovery circuit that's going after the highest dollar ones, you might be recovering 3 or 4 elements out of, say, the 60 elements in that phone. So you are going to be able to recycle, but not for every element. It would be far too expensive. But it is something that's going to make a dent eventually.
All right, good to know.
Yep. And so again, risk is this co-product byproduct. So now some of these minerals that we need, we're going to be dependent upon the demand for base metals, iron, copper, etc., staying high so that we can get the critical minerals that are byproducts needed for the development of our energy systems. So that's another risk. Okay. So now let's quickly move through some of this. I want to get to some interesting case studies that are coming up. So let's just look at critical minerals and energy production. Okay, so this chart on the bottom, you see offshore wind, onshore wind, solar PV, nuclear, coal, and natural gas. These are major energy production systems. And you can see the offshore wind by far is the most critical mineral intensive renewable energy source out there. It uses a lot of zinc. It uses a ton of copper, a little bit of nickel, quite a bit of manganese, quite a bit of chromium, and a little bit of rare earth elements. And we're going to really be diving deep into offshore wind here shortly. But then, of course, onshore wind you can see, as well as solar. So these are all using significantly more critical minerals than our traditional baseload systems like nuclear, coal, and natural gas. When you look over at critical minerals needed in an electric vehicle versus an internal combustion vehicle, it's about 6 times more critical minerals needed to power your electric vehicle. And of course, some of the obvious ones are the graphite, that's the anode in your battery, the cobalt, manganese, and nickel, that's the cathode in your battery, and of course the lithium, which is moving the ions and carrying that electricity back and forth between the anode and the cathode. And so significantly more in electric vehicles. Now, this is a good time to pause and think about this, that we are only going to see an increase in renewable deployment and EV deployment. And there are just not enough critical minerals on the market right now to meet the goals that have been laid out by the auto manufacturers and the utilities deploying the renewable systems. And so just keep that in mind. We're going to hit that a little bit more. Now, want to show you a chart. So this is a very interesting chart to think about. So if you look at the increase in some of the battery material prices, so this is for a typical Tesla Model 3, you have seen massive price increases over the last year, hundreds of percent increases, 100, 200, 400% increases, depending on if we're talking about nickel, cobalt, or lithium. So given that the cathode is one of the most expensive parts of the battery system, just with the current increases we've seen over the last year, it has added almost about $5,000 to $6,000 to the cost of the electric vehicle. So when we're thinking about trying to get electric vehicles down to cost parity with internal combustion engines, the fact that we are short on raw materials is going against making that happen. For the first time in a number of years, this year, multiple EV manufacturers, including Tesla, have now had to raise the price of their electric vehicles. So they're going in the wrong direction and trying to get these electric vehicles to mass market. And of course, utilities, including Dominion, there's a lot of future growth opportunity for us for increasing load by moving to electric vehicles. So there's a lot of incentive for us to make sure that these raw materials are available so the electric vehicle transition can happen, because it's good business for Dominion and it's good business for the environment. And so this is why it's so important that we have a good handle on getting these raw materials to the market. So let's look a little bit more at some data. So these are some demand numbers published by the IEA. So by 2040, we are looking at a 4,200% increase in the amount of lithium from where we were mining it last year. That is a significant number. So last year we did about 100,000 tons globally of mining lithium. In 2040, we need to be mining about 4.3 million tons of lithium. And of course, you can see graphite, cobalt, nickel, even the rare earth elements, 700% increase to 2040. Now, you look at copper, and copper's, okay, so it's a 200 or 300% increase. Keep this in mind. Lithium, we produce 100,000 tons per year. Copper, when we talk about 100 to 200% increase in copper, we are currently mining and producing 21 million tons of copper per year. So to double that or triple that, that is a staggering amount of mining that we need to do just to keep up with the energy transition for copper. And we're going to hit on that a bit more coming up. So now let's talk about refining. So we're just looking at the top 3 countries that refine some of these critical minerals: rare earth elements, lithium, cobalt, and nickel. 60% is a minimum there. So 3 countries are responsible for almost 100% of rare earths, almost 100% of lithium, almost 100% of cobalt, and 60% of nickel. So again, that goes back to, we have it so concentrated where these are being mined as well as where they're being refined, that it's going to create a lot of geopolitical tensions going forward if we don't start building this out domestically in the United States. So this is just, to kind of reiterate some of those points. So just for the clean energy technologies share of these minerals, okay, so we're not even talking about defense, we're not talking about communications. You use rare earth elements to dope the fiber optic cables that we get our internet from. So if you exclude that and we're just talking about clean energy technologies, it's going to be 40% over the next 2 decades for rare earth elements and copper. So 40% of all the copper and rare earth elements used are going to be going just towards energy technologies, 60 to 70% for nickel and cobalt, and 90% for lithium. So 90% of all the lithium mine by the time we get to 2040 will be going towards electric vehicles and stationary storage. So there is a huge demand, and that could be pushing out some of the consumer electronics, some of the medical applications of lithium, and others. So there's still a lot of competition from other industries who need these critical minerals as well, not just energy. And so mineral demand from EVs, as I pointed out, you're looking at 3,000% collectively, lithium over 4,000, nickel and cobalt 2,500%, and like I pointed out, copper will double to almost 40 million tons here over the next 15 years. That's incredible. Mineral demand for power generation increasing by 300%, with offshore wind taking the lead. We're going to really deep dive into that here soon. So here's some other interesting food for thought. Humanity has mined about 700 millions of tons of copper to date. The world will need to mine that same amount in the next 22 years just to keep up with the green energy transition. So think about that for a little bit. Through the history of all of mining, we're going to have to do the same thing in 22 years. Escondida is the largest copper mine by volume, and it's been experiencing falling grades. It's down in Chile since the early 2000s. So the amount of copper they're producing today is about the same as they were producing in the early 2000s, but they have had to increase their energy consumption by 16 times just to keep up with their copper production because the grades are falling. So now we're thinking about how circular this is. We're going to need even more energy just to allow the mining to happen to make even more energy. And so it's becoming very complicated in that regard, which is why there's such an opportunity for utilities and energy companies to be partnering in the mining space to make sure that all of this can happen. You look at a 1,000-pound electric battery, and it can require 500,000 pounds of raw material. So just moving our electric vehicles, that the world is going to be, demanding here over the next 10, 20 years, it's going to require more mined materials in the next 25 years than was mined throughout human history. It's not just copper, that is throughout human history for all mining. So this is a huge mining story. So when I talk to folks in the energy industry or in the utility industry, a lot of them say, that's the supplier's problem. That's the battery manufacturer's problem. That's the mining company's problem. It's like, no, that is our problem. That is our problem at the utility, because we are one of the biggest beneficiaries of the energy transition because of how the utility model works, where we earn on our investments. And so if we can't actually make those investments because the raw materials are not available for us to deploy our solar and our wind and our battery storage, then we're not going to be growing as a company. So you can see that it is a very big problem for energy companies.
All right, Alex, can I get in a couple questions?
Sure.
Quick, we got a few. All right, Michael Zach asked regarding copper use in the offshore wind. Is that the cables? Why is copper so high?
Yeah, so copper is used in the actual generator. It's coiled up in the generator, but it's also used for the energy transmission. So, I think for our offshore wind project, we're actually using aluminum, but many other projects that are connecting the offshore wind power to the grid use copper. So that's why the copper demand is so high. But in those generators, there is a lot of copper. So hopefully that answers that question.
All right, we had another question, and I think it's actually like this slide that you're just starting with. Is there anything happening in terms of battery technology to help reduce reduce these sort of staggering numbers in terms of specific metals?
Yes and no. So let me move through a couple of slides, and I think I'll answer that question. So lithium, why lithium? Because lithium is light and it holds way more energy density than most other appropriate metals on the periodic table. So if you compare that, you hear a lot about iron air, batteries. They can hold about 40 watt hours per kilogram. You compare that to lithium at 100 watt hours per kilogram. So there's just a lot more energy density. So, and energy density and weight make a huge difference when you're putting it in mobility, right? So that's why there's been a bit more of a transition to some of these flow batteries, these redox batteries, vanadium, iron, etc., because they can take up a lot more space because they're stationary. But again, you have to have a lot more room to build them to get the equivalent amount of storage because of that lack of energy density. Now you're seeing some auto manufacturers for their low-end vehicles where you just want a 100-mile, 150-mile range. They're going to a lithium iron phosphate, LFP battery. But again, you can't get those 300, 350, 400-mile ranges with that kind of chemistry. And so that's why lithium in combination with cobalt, nickel, manganese really offers the most energy density right now. But there is a lot of research going into it, which is also hard because auto industry loves standardization. So as battery chemistries keep evolving and innovating, it's very difficult for these auto manufacturers to lock in and kind of get going on that, mass manufacturing because there are a lot of changes. A couple other minerals I want to hit on, and we're going to deep dive a bit on them. Rare earth elements, as I mentioned, they're used in offshore wind turbines, and they're also used in electric vehicle motors. So they're used in these direct drive systems like we use for offshore wind. And these permanent magnets do a lot. They create large energy products, and they're very corrosion resistant. They can operate at high temperatures, which is very important, without demagnetizing. And they are so strong. In fact, if you put two rare earth elements, magnets together, and you stuck your arm in between, it could literally snap your arm in half. I mean, these are incredibly strong magnets. And for probably 20 or 30 years, they've tried to innovate different elements to outperform these, and there really has not been any sort of movement in that space. It's very complicated to find things that are better than these rare earth elements. Cobalt's used a lot for hardening, aircraft metals, things like that, but they're mostly used in batteries right now because it improves predictability. It keeps the battery from blowing up, candidly. Cobalt is expensive, and there's some humanitarian concerns with it. So you've got these battery companies trying to add more nickel to it. But the way the chemistry works, I won't bore you getting into it, you release a lot more gas when you're using more nickel, which can cause a fire hazard. So the cobalt really helps keep the battery from blowing up, which is sort of a big deal. And then of course, nickel, very popular topic right now in batteries. It's very durable. It's got great energy density. It's a perfect cathode material. And so they are trying to use more nickel due to prices. But right now, you've got it. So think about this. Cathodes account for 25% of the cost of the battery. In 2010, the cathode cost of the battery was only 5%. Okay. So this is going to really, really highlight the challenge ahead. Okay, so now it's up to 25% at a time when we have 300 new gigafactories that are under construction globally. Okay, so we already have soaring prices. We already have cathodes at 25% of the cost of the battery. And now we have 300 new gigafactories coming online. And we literally have a quarter of that in new mines being announced. So you're starting to see this huge disconnect on the amount of raw material available versus the gigafactories being built. In the United States alone, we have 13 gigafactories that have been announced. But keep in mind, with 13 gigafactories announced, we have one lithium mine in production in the United States, and it's a very small one, about 2,000 tons a year. You've got one nickel mine that is so close to the end of its life, it'll probably shut down in 2025. You have one rare earth element mine, and you have no cobalt mines in the United States. So while we are introducing these gigafactories in the United States, we do not have the upstream supply to fund them. So we're still going to be importing from maybe non-friendly countries just to run our gigafactories here in the United States. So let's talk a little bit about lithium. As I mentioned, there's just one in the US. It's a brine operation in Nevada operated by Abel Meyer out of North Carolina. It used to be about 10 years ago that the end use of lithium for batteries, for EV batteries, was very small. Today, it's 74% of all the lithium produced is going towards batteries. The US doesn't import a lot of lithium right now just because when they're importing it, it's usually for the medical industry or very specialty lubricants, things like that, because our batteries are manufactured outside of the country right now. So we don't import a lot of it. But when we do import it, it's usually from Argentina, Chile, and China. Argentina and Chile, they make up the lithium triangle in South America. And that's likely where we're going to see more imports until we have more mines in the United States, to source our own material. So lithium increased 21% compared to 2020 for 100,000 tons. And global consumption in that time was about 93,000 tons. So you can see why lithium keeps going up and up and up in price, because we're only producing 100,000 tons. We're consuming 93,000 tons of it. By next year, it'll be flip-flopped. We'll be consuming, or the demand will exceed what we can actually produce globally. So we have a fair amount of reserves. The Salton Sea in California has got a massive amount of reserves. It's really resources right now. They're not moved into reserves. But we've got a lot of lithium globally. So it's not like there's a shortage of it. It's actually getting the regulatory framework to mine it, even outside of the United States. So I will mention before I move on to cobalt, we do have the one lithium mine, but we've got 5 new lithium projects in the United States that will hopefully come online between now and the next 5 years. Fingers crossed. There's a lot of regulatory issues with all of them. 2 of them in Nevada, both have been shut down temporarily because of environmental concerns. You've got one of them in California in the Salton Sea. That is a very, very speculative technology, direct lithium extraction, but pulling it from geothermal. So you're dealing with increased and elevated temperatures plus a ton of other elements in that geothermal brine. So that's a very complicated, mining process. So there's much to learn, and that's still not commercial there. You have one in Arkansas where they're actually extracting brine from the Smackover, which is an oil and gas area. So they're using these oil and gas brines. And then one in North Carolina, Piedmont has just south of us. And that has also been delayed because of environmental concerns. So cobalt, again, very important, high energy density, very thermally stable. And Congo is the #1 producer at 71%. The next largest producer, the next largest is Russia, and they're only at 4%. 170,000 tons produced annually. And again, we don't import a ton of cobalt, The cobalt we're importing right now is not for energy products because those are built outside of our country right now. It's mostly for alloying for specialty metals in aircrafts, etc. So we've got a lot of reserves globally, but the US only represents 1% of the reserves. The good news is the US has identified a huge resource for cobalt in Idaho, and there's one mine in permitting right now. Missouri and other states, where they have some mines that are proposed for, say, nickel, they will be produced as a byproduct. But for specifically mining cobalt, there's only the one in Idaho right now. But Congo has just such a huge reserve base of cobalt. It's very hard to get away from the Democratic Republic of Congo. And of course, even more controversial, and we're not going to get into it today, is seafloor mining. And it's been estimated that there's more than 120 million tons of cobalt on the seafloor. So we'll save that for another conversation. Nickel, really quick. Let's hit that, and I'm going to speed through this. Nickel is really mostly mined in Indonesia and the Philippines. In the U.S., we import it. We mostly use it for stills. That's the #1 use for it in the United States. But we are recycling a lot of nickel in the United States, so that's the good news. But if you look at this picture, that's a laterite nickel mine in Indonesia. These can be very environmentally destructive. So there's a lot of new technologies coming out in nickel. There's a green nickel mine that will hopefully open in the United States. It's the only one right now that's under construction, under permitting, and it's owned by Talon Resources, the Tamarack mine, and they will actually be employing carbon capture and sequestration, which would be incredible. They'll be storing a ton of CO2, and then they'll have no tailings impoundments. They've got some very neat research on how they can actually mitigate those tailings impoundments. So some neat things in the green nickel space are coming out. So let's talk really quickly about rare earth elements. Rare earth elements are mostly produced in China, 61% versus 16% here in the US. But you can see a lot more countries are adding reserves for rare earth element, especially after 2010, 2011, there was a skirmish between China and Japan, which led to export quotas and some serious issues. So that caused some price increases. That really kind of opened up the political part of rare earth elements. So rare earth elements are definitely very important and very much concentrated in China. As far as import goes right now, we hit a peak of import reliance from China at 92% in 2006, and today we're down to about 78%. Okay, let's get into the good stuff. So rare earth elements from coal and coal ash. So this is something that could really make a difference that utilities are focused on, or at least some of them, including Dominion Energy. Rare earth elements are found in coal. We have a lot of coal in the United States. So the DOE has put a ton of money, ton of research into figuring out how to extract rare earth elements from coal. They get in there through various geologic processes I won't bore you with, but they're very low concentrations. Compared to, say, a big deposit, like the Mountain Pass in California, that might have 10,000 parts per million in a given volume. In coal ash, you're like 300, 400, or 500 parts per million. So you've got a concentration issue, but you also have a huge resource with our coal ash. And it's been demonstrated in lab and pilot scales that these rare earth elements can be extracted from coal ash. And so while there's no commercial operations to extract rare earth elements from these coal products, prices have increased substantially over the last 2 or 3 years. There's a lot of DOE support and a lot of really cool research, including some things we're doing at Dominion Energy. And we believe, and hopefully in a few months, I'm updating everyone on a neat project, but we've got a very innovative technique that we think could change how rare earth elements are extracted from coal ash. So more to come. So really quick, want to conclude with a fun case study that really hits home why utilities should care and take it very serious about the critical minerals needed for the energy transition. So this is from our investor slides. We will be deploying 22 billion in zero carbon generation between 22 and 26. So 10 billion of that is in offshore wind. That's going to require critical minerals. 6.5 billion in solar. It's going to require critical minerals. And then over $500 million in energy storage, of course, going to require critical minerals. But let's focus on offshore wind right now. We'll be building 176 Siemens 14.7 megawatt wind turbines by 2026. If you look at the East Coast, it's been projected and in some cases mandated, we'll have about 20 gigawatts of offshore wind on the East Coast by 2035. So now you're up to 1,630 of these turbines offshore by 2035. The IEA estimates that global offshore wind power will be at 2.9 or 2,900 gigawatts by 2050. So scale that up. We're talking about almost 200,000 turbines to meet this ambition. Why am I bringing this up? Why is it important? Here's going to be a fun little thought experiment. Okay, so don't focus on all the numbers, but if we just look at Dominion Energy's offshore wind project, it's going to require almost 88 million pounds of selected critical minerals. This doesn't include all critical minerals. These are selected critical minerals, 88 million pounds. So if you look at world average grades of these commodities, that means that we will be responsible for our project moving almost 9.5 billion pounds of earth for our offshore wind. So to put that in perspective, it's like, well, I mean, what does 9.5 billion pounds of rock look like? If you've ever seen the Empire State Building, it's the equivalent of 13 Empire State Buildings standing side by side. That is the amount of mining just for our offshore wind project. So that is why it's so important that utilities take a lead role, making sure the mining is done sustainably, it's done equitably, and it's done with minimal environmental impact. Because at the end of the day, we are the ones deploying this energy. And that's why when McDonald's sells a hamburger and there's something that's, something bad with the cows, McDonald's is the one that's in the limelight, not the person who's ranching the cows, because it's our product that we're offering to the public. Now let's look at what this looks like for our ambitions by 2035. Now we're talking about 817 million pounds needed for offshore wind on the East Coast by 2035. And that's the equivalent of 120 Empire State Buildings worth of mining and dirt moved and processed to accomplish that goal. Worldwide, 14,373 Empire State Buildings worth of earth moved to accomplish our goals of transitioning to clean energy. In the perspective of worldwide reserves, for just offshore wind, it's not huge, but for zinc and copper, I mean, we're talking about 6%, 3% of the global reserves that will need to be used just for offshore wind. And we're only talking about one of these critical minerals, okay? So now we're just about there. We've got 2 slides left. This is just a fun visualization if you've never seen the Empire State Building in person, but if you're some of our friends from Utah or for the West, or if you've flown into Salt Lake City, you've likely flown over the Bingham Canyon mine. It is one of the largest open pit mines in the world for copper. And there is a picture of the Empire State Building sitting at the bottom of the Bingham Canyon pit. So imagine 12 of those Empire State Buildings sitting at the bottom of the pit. And then think about the size of the pit. That is a huge mine just for offshore wind. Now imagine putting 120 Empire State Buildings in there. You would basically be having the equivalent or larger open pit mine just for the critical minerals needed for offshore wind on the East Coast by 2035. So this just really puts it in perspective that utilities will be responsible for moving earth. And that is why it's so important that we are involved in making it as sustainable as possible. So on that note, what can we do at utilities? Well, first and foremost, we need to be supporting domestic mining. Why? Because we have some of the best environmental standards and regulations in the United States where we can do this safely, we can do it environmentally friendly, and we can do it equitably. So we should be wanting to do made in America for our products starting now. The mining sector does account for 2 to 11% of all the energy consumption. So the energy sector should be working close with these mining companies to make sure we're producing them with clean sources of energy. Energy companies should consider investing directly into domestic mining projects, bring their capital and their expertise. You want to know why that's not crazy? Because look at the auto manufacturers, the auto OEMs, Ford, GM, Tesla, Volkswagen, BMW, all of them have now announced direct investments in mining companies or mining operations because they understand that if they are actually going to get their product to the market, they need to ensure that there's enough product out there to make it happen. utilities and energy companies should be no different. We should be very much supporting this so that we ensure we can make our investments in these energy sources and know that the materials are there to do it. In fact, Wood Mackenzie recently came out with an article 2 weeks ago saying the exact same things, that they're shocked that these energy companies, utilities, et cetera, have not joined the auto manufacturers in ensuring that we've got the capital to make sure we've got the supply needed. And next, we should really be making sure the vendors that we're working with, that they have locked in long-term production supply contracts, that they're not buying off the spot market, et cetera. And so that we can really have some predictability in the capital costs as we deploy these projects. So we don't keep seeing price increases as more and more demand for these critical minerals continues to drive prices up. And lastly, I believe that utilities, just like Dominion Energy, we're looking at how might we extract critical minerals from a waste stream like coal ash. What a great story. We've got an environmental liability that we can turn into new revenue for our ratepayers and offset that liability cost. Such a neat project. But you've also got other utilities like Berkshire Hathaway who have geothermal resources in the Salton Sea. They're actively looking at how they can extract lithium from that brine. So there are opportunities for these utilities to actually contribute and play in the critical mineral space as well to ensure we've got the amount of resources needed to build out our energy future. So with that, I want to thank you all for listening. Hopefully you learned a bit about some of the critical minerals needed for the energy transition, and would be happy in the last 5-10 minutes or so to answer any other questions.
All right, Alex, thank you so much. I think there's actually been an interesting, conversation kind of going back and forth. And I think part of it, there's a big part of it just seems to be, I think the same reaction I had, which is you look at the sheer scale of what we're talking about doing, and does that make you say to yourself, man, we should be looking at some other things too, like nuclear and geothermal and what, anything, how do you think of it in terms of, yeah, we're going to need to do this, but also just given this scale, the impacts required, does it make you think we should also be doing more to investigate opportunities that don't involve critical metals and minerals?
Absolutely, and this is my opinion, not necessarily the companies, but yes, all of the above energy approach. Because at the end of the day, if all we're doing is deploying wind, solar, batteries, we are going to have a serious critical mineral challenge. While you're swapping carbon emissions for these renewable energies, you're introducing potentially environmental destruction, depending on how it's mined. And if it's not in the United States or a Western country, there's a good chance that their environmental standards are much lower or non-existent. Take Indonesia, for example. They just banned 1 or 2 years ago actually getting rid of all their tailings into the ocean for their nickel mining project. So there would actually be beaches and bays that were blood red because they were doing all of their disposal straight into the ocean. And so it's not just in China that you see a lack of these environmental standards, all across the world. So yes, doing geothermal, getting into nuclear, natural gas, of course. We need these very strong baseload supplies, but each one of them has their challenges, right? So that's why the all of the above approach is going to be very much necessary.
And I think one other question that we sort of saw a couple times is just if we are going to try and develop this in the U.S. and this is probably maybe something you can't answer, but how much do we see things held up just by kind of environmental opposition, right? That the same sort of opposition, the political opposition, I guess, right, which held up so many other sort of energy projects, whether it was fossil fuel projects or even like wind projects in Virginia for a long time.
Yep, that is literally 100% the number one problem right now. So as I mentioned, and I've got the number right here, 1, 2, 3, 4, 5. So 11, 12, 13. I count, and there's more, but 13 critical mineral mines that are in the permitting phase here in the United States right now. Some of them have been in that permitting phase for over a decade. And so it is a very, very big problem. On one hand, you have environmentalists calling for a transition to renewables, but some of these same environmentalists are not allowing the permitting to happen because of certain species or endangered species and things that are important that we need to be thinking about. But here's one thing that I think is so important for people to remember. We did not determine, we can't decide where these geologic resources are. These resources are where they are. We can't move the deposits. So it turns out that some of these deposits are in sensitive areas, but at the end of the day, the geology dictates where we can mine these resources. And so unfortunately, it turns out that very cool and unique geology that create beautiful surface features are often the same geology that's happening in the subsurface that set up these ore deposits. From a structural perspective, a tectonic perspective, they all work together. And so oftentimes that is the case, but we can't pick where these deposits are at. So it's not like we can say, hey, let's not mine these lithium, deposits at Thatcher Pass in Nevada because we've got this endangered species. Let's go somewhere else in Nevada, or let's go somewhere else where we don't have this endangered species. And unfortunately, the ore deposit's probably not going to be there.
All right. Well, a lot to think about, everyone. So thank you so much, Alex. Really appreciate it.
Yeah.
Thanks to our DEIC sponsors. Thanks to Dominion, Town of Ashland, Hanover County, and VIPC, Virginia Innovation Partnership Corporation.